Yeah, so today I would like to present few projects where we try to study water in different environments and particularly anisotropic environments. But before I start, I think yeah, normally people don't start from my undergraduate in Argentina, but I expect normal present. I am from here from Argentina. If you don't know where it is now, how you know it's kind of the end of the fall. And if you have the chance ever to travel abroad and you can resist the travel flight of 15, 14 hours from here, you will be amazed by all the cultural things we have, a lot of uh, dancing. This is tango dancing, which is really famous. We also have our famous team, which is called Mate, and we share, which is, I think, a South American concept. We are famous for the grill, so the good quality meat. We have some kings, and we have some queens, and we used to have a pope and many other things. So if you have the chance, I really encourage you. But I think you are here not to hear about the travel agent or advice. You are here to talk about science, and let's get into that. I think for this audience, I don't need to really convince or work hard to tell you that water interfaces are really important, that we cannot overestimate the impact or relevance. So I think maybe the obvious thing to look at is our favorite planet. And just looking at that, we see that it's covered by water interfaces, and then it's indeed 70% of the Earth's surface is water. And I always like to show these two examples. Uh, because of the following. So here we show basically what happens when some ocean waste splash with rocks, and then the particles and aerosols. And then what happens, people are now confident that many of these particles work as really substrates where many reactions can take place at this interface of these droplets. And without these water air interfaces, in this case, we will have a completely different composition in the atmosphere. And therefore, if we can understand this kind of interfaces, we have a good chance to understand our world and the ecosystem we live in. And this is just another example of a little bit more complicated reaction happening again at the water air interface. So even though it's super fundamental, we are still trying to understand this more deeply, because the hope is the more we understand, the better are our models, the more predictive, and the more we can, for example, mitigate climate change. Another very fundamental, probably the most fundamental reaction we can think about is the water dissociation reaction. And I will be talking a little bit about this. Again, I think it's not hard for me to justify the importance and provenance of this reaction. Basically, this governs the acid-base chemistry. So everything that goes in acid-base at the catalysis in the industrial sense really relies on this in one way or another. If you're interested in the climate change or understanding our climate, we need to understand the CO2 dissolution in oceans. And of course, this acid-base equilibrium plays an important role. Also, we familiar with atmospheric chemistry, how the protons and the water is associated in these droplets, which can really change the pH, and therefore the kinetics of reactions in the atmosphere is really something we still don't fully understand. And then lately, I've been working, and my group now is pretty focused on electrified interfaces. And here, I think if you are a chemist, you might remember the Nernst equation, and if not, that's fine. But basically, we know that if you change the pH, you change the electrochemical rates by many orders of magnitude. And particularly understanding the pH not in the bulk of the solution, but rather close to these interfaces is still an open question, and very challenging one. So with this very short introduction, due to the focused audience that I have today, I would like to basically talk you about two different projects or two different stories. One would be the interfacial structure of triple electrolytes in a clear solution, and the other one would be related to the water dissociation in really non-canonical environments. First, I will talk about what happens when you have a strong electric field, and then I will also consider how this reaction changes when you go to sub-nanometer nano-confined. I know that there are a lot of experts on the SFG in the audience, but this is for the non-experts. So the first project I will be talking about a little bit about sound frequency generation. So this is a non-linear second order spectroscopy where, to put it simple, we basically overlap a visible light and an IR pulse in time and in space to get a signal of the second order generated signal. So you see here that I am putting it with my very sophisticated PowerPoint skills, my IR pulse, my visible pulse, and then if you do things correctly, you will have the emission of the signal, which has double the frequency, and that's called that gives the name sub-frequency generation. And this spectroscopy has a lot of important features. The ones we care about is that is molecular specific. In this sense, this is because if you hit with your IR pulse the vibration of the molecules, you have a huge enhancement. So to some extent, you can think this as an IR or a Raman, but this is not quite that. And one of the important things that, and while Ellen is working on this and many other people are working on this, and I find this really important, is this technique, due to the symmetry rules, is always sensitive to interfaces. And this, if you are wondering why, this is a second order susceptibility. That means that if you have an isotropic media, due to symmetry, this signal is zero, and naturally interfaces break the isotropy of the system, so you have something that is surface specific. Because I will be showing a little bit this spec, I think it's good if I introduce this very quickly. So this is, okay, the y-axis is not there, but here I am showing the imaginary part of this second order susceptibility, which from now on I will call chi2, as a function of the IR frequency pulse. And you can see some interesting features. So first, this horizontal line is the zero line. So the different to IR Raman, we have information about the sign, and this sign tells you about the orientation. So if we look, for example, at the high frequency peak, this is normally attributed to free OH water molecules, free OH, because they are not forming a hydrogen bond, and because they are not forming a hydrogen bond, they are very large frequency and also very comparatively narrow. And as I said, the sign is because the water is pointing in this setup towards the air. So if the transition dipole moment points towards, let's say, up, or is positive, then we will have a positive signal. And then if we go a little bit lower in frequency, we have what we call, broadly speaking, the hydrogen bond region. And because we have a negative signal, we know that in average, all these water molecules that are forming hydrogen bonds are in average oriented towards the band. Okay, so let's get with the electrolytes. So if you open let's say textbook, so for example, I pick this theory of some frequency generation spectroscopy, and we go I think to chapter 7 or 8, and we want to understand how ions behave at interfaces. Normally, you will say, well, in almost 100 years ago, we have this very nice work by Onsader and Samaras. Probably I'm mispronouncing the name, but it's fine. So if you just do classical electrostatic arguments and you have a water air interface with the electric constant of A and 1, what will happen is that you will have an image charge, and that will mean that because the charges of the same sign, this was believed for many years, that the ions will be repelled from the water air interface. However, in the early 2000s, when molecular dynamics with polarized force fields started to become mainstream and really accessible with the computational power, people start to see different behavior. So here, for example, I show also a seminar paper by Junger and Topalas. Here on the left, I show you the molecular picture, and on the right is the density profile. So you can see that, for example, if I look here at the sodium iodide, the iodide are these violet balls, and you see that we have a huge accumulation at the interface, and then you form what the people call a double layer. This is a little bit of stealing a concept from electrochemistry or charge interferences, but still you have an anion and a cation, and if you go to other salts, you have the same. So people were saying, well, maybe Gonzalez and Samaras was really a continuous model. They didn't include polarization. So if you include polarization or polarized ions, you might have this really different behavior, right? Because this would be really available to react with whatever you have at the air. So then if you continue with the same book and go further in that chapter, so Morita tells us that basically you can have normally two scenarios. So on the left, I'll show you, for example, the case of HCl, where you have the protons are more surface active, so they really go to the interface, and then you have, for example, chloride ions that go on the subsurface. And what happens, as I said, it forms what people call an EDL, and that generates a local field that orients water, and now everyone is a SFG expert, so we know that if you have an additional orientation of water pointing towards the bulk, then you will have an additional signal in the hydrogen bond region. And then people measured the SFG, and they actually saw that, so they were really happy. And then if you take another, like sodium iodide, then you will have the other behavior, the field goes in the other direction, and then you will have a change in the hydrogen bond region that is positive. And these are a little bit noisy measurements, but believe me, if you look closer, you will see that. So everyone was happy. Then Gonzalez and Samaras were then clearly, but then the theory was a little bit debunked to some extent. So after I finished my PhD, I did a short stay with the Chabon and Vicky Nagata and Vance, and then back then they had these interesting measurements. So here I'm showing you the electrolyte signal. The SFG signal for 3 different electrolytes. In all the cases, I show you the water in black, and then I show you the HCl. On the first one, cesium fluoride and sodium chloride, and you can see that in the case of the HCl, so on the left, this is what people expected, so nothing new there. But if we go to cesium fluoride, you see that the behavior is a little bit different. So you have a little bit of positive change and negative change, something that cannot be explained by the overall theory at the time, which is basically either a negative or a positive. And then if you look to sodium chloride, which is arguably the simplest electrolyte, you see a small change in the 3200 and no change there. So we basically found that even for the simplest electrolytes, the textbook knowledge was not enough. So here I always say that they look for a great theoretician. They called him. This person was not available, and they settled with me. So I am here skipping many details, but just to give you a glimpse, what we do is we run molecular dynamic simulation, in this case using machine learning iteratory potentials, and we have our trajectory. Along our trajectory, we connect dipoles and polarizabilities, and then we can give you the correlation function of polarizability and dipole moment, and we get the access to the Kaiju state from. There are many details I am missing out, so I'm happy to explain further if there are people interested in the audience. And here, so this is just maybe one slide of another paper. So we were collaborating with David Wilkins from the University of Petlas. So we did some hybrid machine learning, in the sense we use a machine learning model for the potential energy surface and another model for the dipole and the polarizabilities. And we didn't make a one-to-one match, but here I show you what is the reference and what is the machine learning model. So we were quite happy. So when we really need to evaluate this equation, we now have the tools to do it quite efficient. But okay, for reasons that will become clear in a moment, let's focus here on the sodium hydroxide. So this I haven't shown you, so let me introduce you. So there, y-axis, imaginary part of Kaiju, x-axis, frequency domain, black is always water, and with different colors, you see different concentrations of sodium hydroxide. And here there are 3 changes that I would like you to focus, which here I put in arrows. So the first thing is the free OH region. We have no change, and the free OH, as you remember, is this Dunley OH bond, And this suggests that there is basically nothing displaced in this free OH. So this NaOH is not going to the interface. That's one sign. And the other thing we have is this positive and negative change of the signal at the same time, which again cannot be explained by the simple double layer approach. So I run my machinery, run my models, burn some CO2 on the way, and then here I got my SFG spectra, which is not great, but I was super happy because it captured the three main trends I was looking for. The free OH doesn't change. Here we have a positive change in around 3500, and then on the lower frequency we have this broadband, and then we have the opposite change in signal with concentration. So after I cut this, I said, okay, I can trust my model so I can have a closer look of what's going on. And then, so for you to have an idea, the first thing you normally look at interfaces is the density profile. So on the left, I show you the density profile. Oxygen is the oxygen of water, and it's black. And then you see that sodium and hydroxide are really repelled from the interface, at least few angstroms. And then if you here on this plot, I show you the orientation. This is normally plot as the cosine of the angle of the dipole with respect to the surface normal. What we need to know is at the cartoons that I put there. If this is positive, water is pointing up, meaning towards air. If this is negative, water is pointing down. That means towards bottom. And here I'm just showing the only two curves, and this basically the blue curve is basically waters which are next to sodium atoms, and the waters which are next to OH minus. So you can see that sodium somehow orients waters positively and OH minus negatively. But what was also quite interesting is that here they just put a gray area also to help you guide the eye, is that from 0 to -4 angstroms on the first really monolayer, we have a very tiny amount of ions, but the water in that region is highly oriented. So somehow we have ions in the subsurface that are oriented the topmost layer of the water. Another interesting thing we can do with the simulations that in experiments is, let's say, impossible or much harder to do, is start to dissecting the spectrum. So I can take my signal, and then I can separate whatever comes from waters which are next to sodium and waters next to OH minus. And if you do that, you have the composition here on the bottom, and you see that water next to sodium appears on the 3500 peak, and it increases with concentration, becoming more positive. And on the left, here on the right, we see that the water next to OH minus is oriented negatively. So here a negative signal, and then it's on the low frequency region and give you this continuity. So now we can really explain all these positive and negative changes are basically due to water in different environments. So with all this information, so with the fact that the free OH is unperturbed and the water, sodium and OH minus are repelled from the interface and they align water molecules, we came up with this very simple 3-layer model or stratification model. And then I was really happy. I was saying, well, the NaOH is a very nice example. Let's write the paper, the breakdown of the EDL. But then we say, well, maybe we can try to understand this and come back to the original data where we have so many electrolytes. So here's something I was doing without telling you. Sorry for that. Is that I am implicit assuming a linear combination. So I would say that the solution is signal comes from water and electrolyte, and the electrolyte, so water next to, let's say, water and water next to electrolyte, and then the water, the electrolyte part comes from water next to cation and an ion. So here I show you a bunch of electrolytes. So here we can easily take out the pure water signal, and we get what I call the electrolyte. And here comes a little bit of a tricky part because experimentally it's really hard to disentangle. So what people do in the SFG community is, to some extent, you can approximate the cation signal as a square root of IR Raman. And this, if you remember the equation, you can think, because we compute the correlation function of dipole and polarizability. If you will compute Raman, you will correlate polarizability and polarizability for IR with dipole. So this makes some sense. But still, it's a rough approximation. And then, because normally the cation is not really forming hydrogen bonds with water, right? And it's not perturbing the OH bond so much, we can assume that it has basically the bulk spectral shape. This is a very rough approximation. And we say, okay, let's do this approximation, see what we get. And if we get something that makes sense, we will be happy. And then we can try to extend this a little bit further. So if we do that, we get the anion contribution. And we were quite pleased to see this because of two reasons. First, the signal is negative, which was predicted by our stratification model. And then what we see here is in progression from fluoride, chloride, bromide, and iodide. And you might know that chloride forms the strongest hydrogen bond, and then the iodide the weakest one. So then this basically follows that. So it's completely consistent. But still, we were not really happy because this approximation is quite rough. So we say, okay, can we find more experimental evidence? And we can. So what we did is, some big person doing experiments with what wasn't me. Poyan measured other electrolytes with the same anion. So we did the same analysis. And here I show you the anion contribution for cesium chloride and for sodium fluoride. And you see that it's largely similar. And here on the bottom, you see sodium chloride and magnesium chloride, and you see that it's largely similar. So this, we really strong evidence that the model is largely appropriate. So this is me using ChatGPT. So I hope that in this part of the talk, I convince you that this electric level layer does not apply for neutral, non-charged differences. And for most common electrolyte systems, we have an ion-free layer and electrolyte solution. Okay, 20 minutes. I am on time. So now I would like to change gears a little bit and move to water dissociation reaction. I started looking at this because I found a series of papers that look at this experimentally. So they use something called bipolar membranes, you see here on the top left, where basically they put a polymer that has fixed anion charges and a polymer that has a fixed cation, positive charges, and they stick them together, and basically that's a bipolar membrane. So because you have fixed negative and fixed positive charges, you can allow only the counter charge to go through. And then they can measure, they can put a thin oxide layer, and then what you can measure, for example, the hydrogen evolution reaction, and then depending on the conditions, you can make sure that the bottleneck of this reaction is the water dissociation in the middle. So you measure current, but then what you're measuring is water dissociation. And what struck me is here in the middle, they did a very simple Arrhenius analysis. So on the Y, you see the variant of the rate of the current versus 1 over temperature. And they measure these at different over potentials. So they apply no different bias potentials, and then they measure this. And you see that all these curves from lower potential violet and on the top, peak, higher potential, they're all really parallel. So that means if you just do a simple Arrhenius analysis that tells you that the slope is proportional to the activation energy, it's telling you that you change the voltage and the activation energy is not changing. And the reaction is getting faster because if you want here, the y-intercept is changing, which is normally associated to the activation entropy. So, and this is really profound. You are making your reaction faster, not because you are lowering your activation energy, as what in Polymer or many textbooks will suggest, but because entropic effects are really accelerating this reaction. I was quite excited. I said, okay, this is one system, one group. Maybe they have an artifact. I am 10 years away at least to be able to simulate something that resembles this. So maybe I should not get super excited. But you know how it's life. So I found another set of papers, and let me just quickly introduce you this figure. So here they measure as a function of temperature, and they get for each curve, they get activation energy and y-intercept of activation entropy. And in this paper, instead of plotting the temperature, they get the curve, they get two values and put that in activation energy in the x and look at the factor or activation entropy on the y. Here, for your convenience, I shall put the isotope current lines. That means that if you move along this line, you will have the same current or same rate because you have a compensation between enthalpy and entropy. So let's say we measure our reaction at 1 over potential and we have that point. If you open a textbook, you will see, or you will expect that the activation energy will go down. So you will expect that you will move here faster. So you go from this isocurrent to this isocurrent. So you are becoming faster because the activation energy is decreasing. You increase your potential lower and lower. These are what people measure. So these are different oxides that they put in the inner region between the bipolar membrane. And let's probably let's pick one, for example, titanium oxide. So here different colors are different potentials. So here the value is 40 millib and the largest one is 200 millib. So increasing our potential, and you see that the line is vertical, not horizontal. So exactly the opposite as we will state, and this is appears for many oxides, and therefore iridium is really different, and this is because it has metallic behavior, and we can discuss that later. So I said, okay, let's try to understand this. What do you know? What do we know about water dissociation and electric fields? And it seems we don't know much. So I said, okay, let's start with the baseline. So I'll take a box of water and apply an electric field, and then I want to test this hypothesis. Expectation is the change. Basically, the field will use a change in enthalpy, which is proportional to the change in dipole moment between the reactants and the transition state. Basically, if this has a larger dipole, then you are stabilizing more the species with larger dipole, not a crazy idea. So again, here I'm skipping a lot of details, but we can run amination D, do some enhanced sampling, compute our free energy of hard water and 2OH minus. Here I got lucky and got, so here pKw 14.7, which is a free energy of 84, and the experiment is 82. I will not claim that relativity T3 is great, not with this, with some of the people in the audience particularly. This is a great example of error cancellation that I think this is good enough to see trends, and as you will see now in the moment. So here I can repeat the calculation and get again the free energy for the dissociation of water as a change as a function of temperature. In red, I show you the amination D, and in red, in orange, the experiments that they are largely in agreement. Again, cancellation of errors, but the trend is robust. So I was quite happy. This was without pill. So this basically validated my setup, and I said, okay, now comes the fun part. An important thing. So if you don't have pills, water is enthalpically and entropically unfavorable, right? So you have a positive a change of internal energy, and here we have a very large negative entropy change for this reaction. So we can, this is the same figure without field. We can apply a very large field, and we start seeing this change. And then if we apply a slightly larger field, then we have a completely change the free energy of energy. If we shall pick the free energy as a not change in internal energy minus temperature, change in entropy, we see that we have a positive slope, which means negative entropy, to a negative slope, which is positive entropy. So in the next few slides, I will try to give you an idea of what's going on. So the first thing I have to tell you is that in my simulations, when I start applying these spins, I start to see a dissociation spontaneously. So here, basically, when I reach 3.35 or 0.4, I have a huge amount of ions in concentration in average. So this means water dissociates and recombines, but this does pretty fast. So in average, I have this concentration. And one thing that we also see is that when you apply electric fields, the water starts to become more structural. So here I try to represent this with what's called the tetrahedral parameter. So here a value of 1 means water is completely tetrahedral, and 0 is completely non-tetrahedral. The orange is without field, and you see that if we go orange and the different tones of violet, you get larger, closer to 1. That means water gets quite structured, and then 4.5 a 0.41, then we have a withdrawal. So when we have a large amount of ions, it looks like this is going against this stiffen of the field. So the field at low fields, water gets more structure, and then at large fields, when we have dissociation, it goes a little bit more mobile. And this is also if you measure other things like hydrogen bond atoms per water molecule. So it goes up. When you form hydrogen bonds, you release energy, but you also decrease in entropy because everything is more rigid. And then when you start having ions, we have this drop. So we thought, okay, maybe the ion concentration is kind of an important thing. So we did this simple experiment, computational experiment. We separate reactants and products. So reactants, I do simulations where I don't allow for the water to dissociate. And then you see that the hydrogen bond increases with the fin. And here I run another simulation where I put either a proton or an OH minus. I don't know a fit, and you see that basically the presence of the ion doesn't allow the water to build this structure. So we can think that if we look at large electric fields, the reactant side has a very structured, very large amount of hydrogen bonds and has a low entropy state, and the products have a comparatively high entropy. And then when you compute the difference of the reaction, you will have a positive one. And one way of understanding this, if you're thinking, okay, this is how the mechanism works, it's very simple and I feel intuitive. If you have a proton that will jump to the next water molecule, imagine here you have an electric field that is aligning this water molecule here. After you have a hydrogen jump and you have a new proton, the water is aligned anti-parallel to the field. That means that this water is unhappy, is unstable, and would like to reorient and to relax to the new orientation. And during this reorientation, really is breaking all the hydrogen bonds. And if you think that the proton is going a little bit one after the other, that means that this is kind of destroying this hydrogen bond network. So let me probably summarize this quickly in this field. So I show you here the entropy. These are arbitrary in values. So there is a shift that I don't know. All the theory is relevant, all the differences. So if we start with water, no field, we have random orientation. Let's pick a value of 200 kilojoule per mole. If we now think again on water, but with large electric field, so this will be reactant side. We have water alignment, and that reduces the entropy. If we think in products, when we don't have field, we have that the proton and the OH minus are really coordinated really strongly the water molecules, and that decreases the entropy. That means that we have a negative entropy change. But then when we have protons and field, we have this bowling kind of effect that the proton and the OH minus goes and disrupts the hydrogen bond accretion, and we have an increasing entropy that gives you the high increase. And of course, this is a little bit far from the experiments I show, but we are going into that direction. So this was the first stepping stone. And I think in the last few minutes, I would like to also continue a little bit with this water dissociation. And I would like to briefly talk about what happens on the water dissociation under nano-confinement. And this is relevant because these days people can really aggregate these devices where you put graphene and then some spacer, then another graphene or HPN, and you can have nanochannels. So for all these things, you can really have interesting properties of ion transport or even reactivity under this nanometer regime. So again, the question is very simple. What is the water dissociation in these nano-confinements? So the first thing you do as a researcher, you look into literature. And now I should be careful on what I say because I am being recorded. But yeah, you find this this nice paper. Dominic Marx is a very famous person of the field. He says nano-confinement in split pore enhances water dissociation. Okay, that makes sense. You keep looking. You say, well, let's look what the chemistry community has to say. You find another paper by someone who's really well known, Francesco Paisani, and you read nanometer confinement suppresses. So the completely the opposite behavior. Okay, you say, well, these are people, we are from Europe. Let's look at the European journal. We don't like the people from overseas. So we go to Angebanter. and you find again some people use artisanally and potentialists, and then you see water is insensitive. So basically, you can choose whatever you want. So we say, okay, maybe we can somehow try to help. Maybe we can try to make sense of this really disparate results. So here, yeah, this was the work done by Xavi when I was in Cambridge. So basically, this is a graphical summary of those past works. So it can decrease or increase the number of the P and W by a few orders of magnitude. And what we noted quite early is that when you have this sub-nanometer nano-confined, people normally, in most of the cases, they let this height relax, but they stick with some number of other molecules, and this is not properly equilibrated. So if we shove over the dependence on the water density, then you see that you can completely change the pKw. So here I show you, so this surface density is the number of oxygen per cross section, and you see that it changes 3 or no, 4 units with 20% of the density. So basically, we did our homework. Sorry, before I go, if you go in the literature, these are the density profile, the surface density they use, and you see that goes from 0.09 to 0.11. So people were not really taking care of this appropriately. So basically, we did that. So for this, we had to run really large systems. So there are some technical issues because at the moment the code we were using was not really efficient to run in parallel. So we had to use a CPU implementation. That's, if someone is interested, I can explain. And basically, we had to run simulations with 30,000 atoms and really do deep increase in size and converge this to extrapolate. And then we can get the equilibrium density. So here, basically, what I will show is here's the pKw as a function of chemical potential that we compute or the corresponding bulk pressure. So this is the pressure that you will have in a reservoir that equilibrated will give you a density in the nano-confined system. And this is, if you compute the dissociation at that density, this is what we get. And then if we add no bulk, we see almost no change. And this is quite surprising because here you have one monolayer of water. So this cannot be more far from bulk water. And you see the water dissociation is really, if you compare comparable the dynamic states, you have the same water dissociation. So I thought we shed some light on that. And then experimentally, they always, and then I am almost finishing. Experimentally, they can also do other setups, not only two layers, but they can put graphene, and then they can put some water, and they can on another layer of graphene, and they have this droplet of water. So they will say, okay, what happens here? This is fundamentally different because this is not integrated with bulk. So here you can have a different density, a different pressure. If you compute the pressure, this is in the order of gigapascal inside this droplet. So then we ask this question: what's the pKw in the core region and in the edge? So if we start first on the droplet core, you see that we have a decrease in the water dissociation, and this is due to the pressure that builds due to this. So this van der Waals interaction presses and compresses, and if you compute the pressure, you get a really large pressure, and this is known. If you increase the pressure, the pKw goes down. If you look at the edge, because you have not the proper solvation shell, so the products cannot be properly solvated, so you have destabilization, so you have an increase of 2 units. And then if you do the same with HPL, because this is also relevant in these nano-fluidic devices, in the core, there is nothing new, so the same as graphene, but if you go to the interface, when you have this curvature HPN, the HPN becomes a little bit more reactive because the orbitals of boron and nitride overlap less. That means that it has a higher local charge, which is more reactive and stabilized and can isort the OH. And if you have a chemical solution that drags the reaction, then you will have, of course, a more favorable reaction. So I hope that in this last project, I convince you that the pKw dramatically depends on the water density, and if you do things properly refrigerated, there is almost no difference, even if you go to the monolayer chip. And if you start looking at more sophisticated or complex architectures, it can really be affected by the boundary effects, the pressure, and you can really tune this chemistry. Overall, I think I just discussed very simple systems. We first look at the interface of electrolyte solutions, and I hope I give you enough evidence, computational, experimental, that for the most simple cases of electrolytes is stratified. And then we started to look at the water dissociation on electric fields. This is relevant because many electrochemical devices really build up with these really large fields close to the interface. So understanding this means understanding the pH, means understanding chemical rates. And then we also try to look at this very fundamental reaction in other environments, like nano-confined. And I convince you that if you do, you have to do things really carefully to get thermodynamic comparable studies to drive conclusions. And with that, I would like to thank all the people that was involved in these projects, the funding, and then before I forget, I am with two colleagues. I am organizing a computational spectroscopy summer school in Lausanne, so not really far from here. And I am super happy and excited because when I was learning spectroscopy, I basically used these books, the Mukamer book, the Hash book, Ross for DDFT, and Bill Shaw, and we managed to invite everyone, and luckily they all accepted our invitation. So we are really excited. So please apply if you're interested. And with this, I would like to thank you very much.